A set of pulleys can be used to reduce the amount of force needed to lift a mass as shown below. And here's this picture of this kind of pulley setup with a mass. If the mass is 74 kilograms, how much tension is needed to lift it at a constant speed using the pulleys? And then it says, given that mechanical advantage is defined to be the ratio of the weight of the mass to the needed tension, what is the mechanical advantage of this system? So, okay, how do we do this? I have to kind of decide like what system I want to analyze. It does say constant speed there though. So I'm kind of thinking like this could be an inertial motion type of situation. But I'm going to redraw this as a sketch a little bit because I want to talk a little bit about like what system I think I'd like to choose to analyze here and how I'm going to think about the forces for it. So let's say here's that kind of rigid ceiling this thing's maybe hung from. And so my drawing is going to be really simple here, I think. Here's one of the pulleys. Here's kind of the string going over the pulley or rope going over the pulley. It's looping around a second one of the pulley that's right down here roughly, and then looping back to kind of the center of this pulley. So that's roughly my drawing. And then underneath that, or kind of hung from that pulley, I'm not going to try to draw all that stuff there, but here is that mass M. And since we're talking about it at a constant speed, I think it might be okay to say in here that we're trying to apply a tension force so that this mass can maintain a constant velocity going upward. Now, something to recognize, if you ask, like, do you think that's going to require more tension, less tension, same amount of tension, as if this mass were just hanging there and you were just holding this thing to prevent it from falling? And my answer is it should be about the same amount of tension. Now, in reality, there might be some drag forces or other kinds of forces in the pulley here, but if there's no like kind of internal like friction, you could say, in the pulleys as they go around their axles, and I don't know, there might be some other forces we're talking about there, but that's the main ones, I think. If that's not there, then the answer is it's the same tension whether this thing is moving or not, because this really is kind of an inertial type of situation. But what I'd like to look at in terms of a system is I'm going to draw kind of a dotted line box here and make this my system. It's going to be the mass together with that pulley. And the reason why I'm making that my system is because I'm going to assume that these pulleys are actually like very low mass, maybe near to being massless. And that's going to allow me to make some simplifying assumptions. And usually real pulleys are designed to kind of be that way. So even for like, systems that do this in reality, they might, they will have that characteristic. You don't want super heavy pulleys. You need them to be strong enough to do the job, but usually you don't want them to add too much more weight to the system. So at least in reality, it would be maybe an approximation, but we're going to assume that it's close enough here. And in that sense, the free body diagram for the system that I've chosen here would naturally have a weight force. But if I ask what other forces should it have, well, the only other thing that this system is interacting with other than gravity is kind of the pulley above it, and it's connected to it by two kind of pieces of string or rope or whatever they are, this one here and this one here. And if I can make the simplifying assumption that the tension force is constant throughout, which it turns out if there is no significant kind of rotational drag in these pulleys, sometimes one would have to say that maybe they'd have to be close to being massless for that as well. But that's a bit debatable. If it's inertial motion, it may actually not be necessary to even assume that. But long story short, I think there's kind of two tension forces here, and that may be a little bit hard for me to draw in my free body diagram, because normally I would say, like, when we looked at like normal forces on feet, we always said let's make them one force. But since in this case we're being asked for how much tension is applied to the rope here, in other words, like what's the force being applied right here. But if the role of the rope, really kind of the role of tension, is in a sense to transmit that force throughout that rope here, then whatever force, whatever F of t I applied there should be equal to the individual F of t's I've put in my free body diagram here. So that's why I've kept them separate in this case, to make that clear, that I'm really after just one of those F's of t's. That kind of makes it, if I look at the idea based on inertial motion that net force is equal to 0. In this case, I think that would look like, since these two forces are basically, the two forces and the two ropes are effectively equal to each other, and I'm kind of, this was maybe slightly slanted, but I'm going to ignore that. I'm pretending they're both perfectly vertical. Then really I've got kind of like the first tension force, but it's identical to the second tension force, plus the gravity force. This is what I would do as a vector equation. But then if I looked at that in terms of y components, these two would be the same. And so I just have 2 times that force of tension minus force of gravity. So that's where I put the minus sign explicitly to indicate that it's pointing down. But that really means that that force of tension should just be equal to half the weight force, half of the gravity force. In other words, half of mg. And that's something I can calculate with the number that's given to me here, because I'm given that mass of 74 kilograms times 9.81 meters per second squared. That is something I can put into the calculator, and it winds up being 362.97, which I think I would just round off to 363 newtons. Now, the second part of this question was about this concept of mechanical advantage. I chose this example because I wanted to throw that out there at some point. It's not something quite as emphasized, I think, in this course as maybe some other physics courses out there, but it's worth running into because it comes up here and there. But it's defined to be the ratio of the weight of the mass to the needed tension, right? So in that sense, maybe I'll just put down here mechanical advantage, MA, is again equal to I think what I called FG, and the ratio of that to the needed tension. Well, the thing to notice is that the tension was equal to half, right, of gravity exactly, and that means these two can cancel, and that winds up 1 over 1/2 actually simplifies to 2. So my simple answer for that second question is just the number 2 is the mechanical advantage. And one simple way of seeing that, I've often thought it's neat that you can tie that mechanical advantage. Even if you have a more complicated pulley system, it usually winds up working in the following way. If you can count the total number of lines or ropes or whatever that are pulling up on your system versus the amount that you're pulling with, which is usually just 1, it is always going to be a ratio of that number to 1. So in other words, there's 2 ropes here to 1, 2 to 1, hence a mechanical advantage of 2. So there it is, 363 newtons and mechanical advantage of 2.